Okay, good morning. Let us get started. Can you hear me in the back? Sounds good. Volume seems good. Hopefully the noise, rattling noise will be minimal. All right. So today we're going to talk about a new computational pattern. We talked about a one-dimensional vector add, and you're doing that now for lab 1. Today we're going to introduce, really the topic is the memory model for CUDA. But in learning about the memory model, we got to introduce a more complex computational pattern. And that pattern is going to be a matrix multiply. All right, so at some point, very soon, we're going to just dive into that. Now, before we go and get started, just a few reminders. Lab 1 is due tomorrow. I know some of you have tried to submit and have either succeeded or failed. And we're still trying to get the submit functionality working correctly. Give us until the end of the day. Okay, so don't be too frustrated. We're close. We'll probably post something on CampusWire when it's ready, so you can, just submit once we post. Okay. Lab 2, we will make it available tomorrow, so that you can get started over the weekend. And Lab 2 is going to be drawn heavily upon today's lecture. Again, matrix multiply. All right, so before we get started, any questions, comments, feedback? Yes?
If we run the subject multiple times, where the graders only count the last one.
Yeah, so the question is, if you submit multiple times, what gets counted? So what we will do is we'll take the final submit that is before the deadline. Okay, so that's the one we'll count. But try not to do that, because it just creates confusion. So when you're ready to submit, submit.
This is weird, but when I tried to look at my history log, it wasn't really clear which one was a successful submission and versus an unsuccessful one. So how do you know whether your submission has actually gone through?
Can you put a post on CampusWire? We'll try to add that, right? So just so you get a flag of which tests passed and so on and so forth directly in the history. All right. That's a feature we need to add. Okay, any other questions? Okay, good. Okay, so there's a few things I want to clean up from last time. And let's start off with this picture again. Okay, so let's get back in the right frame of mind here. We've got something we're doing. To keep it simple, let's say it's a vector add. We've taken that vector add, which simple for loop, going from 0 to n minus 1, and we've blocked it. So we've got some number of blocks that contain some number of threads. So we've taken our long sequence of iterations, and we've created a block, a block, a block, a block. And within each block, we have some number of threads, where each thread, by design, is calculating one output element. Right? That was a choice. We showed you an example of where each thread calculates two output elements. It's the choice. So, in our simple view, each thread calculating one output element is in a block, and we've got some number of these blocks extending to the end of the full computation. Now, what's going to happen, recalling our diagram from last time, each of these blocks is an entity that will get mapped onto the GPU resources. And these resources, we call them streaming multiprocessors, or SMs. And depending on the GPU that we're executing on, we might have a dozen SMs, we might have 1,000 SMs. We don't really know, and we don't want to know. We're not going to write our code specific to a piece of hardware. We want to write it generically. So what we know is we've got some number of these blocks, and those blocks are going to execute on some number of these SMs. And it's the job of the GPU driver to take those blocks and map them in some fashion onto those streaming multiprocessors, those SMs. There is a question.
Can a grid run on multiple SMs, or can it only run on one?
Can a grid run on multiple SMs, or can it run on just one? There are multi-GPU versions of CUDA. Okay, we'll talk about those at the end of the semester. But the idea we're going to have today is that a grid runs on one GPU. Okay, so right now let's keep it simple. One GPU, a grid, lots of blocks. Those blocks end up getting scheduled on those SMs. So now once a block is on an SM, and by the way, a SM can handle multiple blocks. So we can map, in some cases, 32 blocks onto some of the higher or later versions of the NVIDIA CUDA architecture. Pascal, Turing, Ampere are the later generations. Okay, so we can map a bunch of these things. Now, the thing to keep in mind is that from the perspective of the SM, what we want is lots and lots of choice. We want lots of work, but at any point in time, we might choose to put the thing we're working on pause so that we might do something else. So from the perspective of an SM, it's good to have lots of blocks. And I'll explain. Okay. So that's the first step. Take our work, chunk it up into blocks. These blocks eventually get mapped onto the hardware. And the hardware provides all the resources that block needs to execute. Adders, multipliers, memories, registers. We'll talk about those shortly. Now, here's where it gets interesting. So each block consists of some number of threads. Let's say 256, just as an example. We could pick as many threads as we want. We could put one thread in a block. Doesn't really make sense to do that, but we could. Okay, so these blocks have bunches of threads. And let's say 256 threads in the block. Now, kind of what we're going to do is we're going to take these threads in the block and consider them as 32 thread warps. So I'm going to take the first 32 threads in that block, that's warp 0. Then the next 32, warp 1, and so on and so forth. And these warps become the schedulable entities that execute on the SM hardware, which is very different than when we think about a CPU thread. Right? A CPU thread is a single instruction. Well, I guess the GPU thread is also a single instruction, but from an execution perspective, the thread is organized as chunks of 32, these warps. Okay. So when we take a look at any SM at any point in time, we've got its resources, register file, memories, execution hardware. That SM has available to it a bunch of blocks, and within those blocks, a bunch of warps. And within these warps, 32 threads. Do you see that hierarchy? Okay. So, a few examples, right? Just simple ones. You can see them there. If we have 3 blocks, each block has 256 threads. How many warps are there? 256 threads divided by 32, so each block has 8 warps. And because there are 8 warps, there are, within each block, there are 24 warps altogether. Question?
How does the GPU scheduler know when to change the warp that's executing?
Good, let's talk about that. Okay, so he brings up a very good point. So we've got this nice piece of hardware here, digital hardware. And that digital hardware, at any point in time, has to make a choice. I've got all these things that can potentially execute. Now, the beauty is there's no order. I don't have to wait for warp 0, block 1 to finish before I pick warp 16, block 4. By design, there's no order. And how do we know that? How do we know that there is no order across the warps and the blocks? It's kind of a simple question. Yeah?
They're all performing independent operations.
By design, when we coded this, we ensured that all the threads in that initial algorithm were independent, and therefore all the blocks are independent. Right? We could execute all the threads independently. We organize them into blocks and threads and warps, but they can all run at any time. Yes, question?
At a given time, only one work within a block is being run, right?
Yes. Okay, so now let's get down to the nitty-gritty. Let's make sure it's super clear to us. Okay, so at some level, right, if you've ever taken a computer architecture course or know how a computer is organized, at some point, you'll realize that, well, there's really a pipeline. I start an instruction, I continue that instruction, and at some point, that instruction finishes. Okay, so it doesn't matter, it's not the case anymore that an instruction finishes in one clock cycle. It may take many, many clock cycles. But what I'm doing is I have this assembly line where I start the instruction and I keep progressing it forward, all the while starting new instructions every cycle. Okay, so from the perspective of that pipeline, what I'm doing is I'm starting the instructions of a particular warp, and what I could do is on any clock cycle decide, okay, this particular warp, for whatever reason, is seeing some kind of stall. So for example, let's say I start with thread block 1, warp 1, and I keep processing that particular warp for 6 clock cycles, meaning I'm just continuing to fetch instructions from that warp, 32 at a time, for 6 clock cycles. But then at that point I realize, okay, the warp is doing a load, which is trying to get some data from a memory that's very distant. And I'm not going to be able to make any progress on that warp for a long time. So rather than have the hardware go idle and wait, we'll just pick another warp from another thread block. Or a warp from the same thread block. It doesn't really matter. And then we go. And then we go and we go. So the point here is the more warps that we give the SM, the more an ability that SM has to fill any idleness that it might encounter, right? Which is great, because the point of the game here is to keep the hardware as busy as possible, despite things that take a long latency, right? Remember, the name of the game with the GPU is throughput, meaning it doesn't matter how long these instructions take. They could take 1,000 clock cycles. Doesn't matter. because I'm just keeping the hardware fully utilized all the time because I've got so many of these threads. Okay, does that make sense? Any questions on that? There's a question in the back, yes.
So, if the number of threads in a block is in a multiple of 32, does a warp contain threads across the block?
No. No, they will only contain threads within that block, but you bring up a very good point. His question was, and I'm going to paraphrase, what if a thread block contains fewer than 32 threads? Right, I think that's what you're asking. So in that case, we have this warp that has fewer than 32 instructions, or fewer than 32 threads within it. So it's not a full warp. Okay, that's fine. And we're going to see many examples of that shortly. Okay, a few more questions and we'll move on. Yes?
An SM at a given time can handle more than one work, right?
So at any point in time, the simple model we're going to have, and this is true for most GPUs, is that on any given clock cycle, one warp is being fetched from. So one warp is making forward progress. Okay. But within the pipeline, we can have many, many warps currently in progress. Yes?
The question is if, for example, in this example, we take essentially 8 clock cycles to figure out one warp line, because it's repeated later. So regardless of when we're doing those 8 clock cycles, in this situation we're doing 6 now, 2 later.
Yes.
But how does it get optimized if you just clock cycles in the beginning and then how is it essentially optimized?
Okay, because what might happen is after this 6, okay, let's say at point 6, I cannot execute 7 in the next clock cycle. Okay, because maybe I'm executing a divide instruction, and that divide instruction takes some time because of the hardware, the way it's operating. So I can't execute 7, so I could, by design, just say, well, I'll wait. Right? And if I'm waiting, that's wasted time. So rather than waiting, let's do something else. Anytime we wait, let's go do something else. And that is the principle, the simple principle in the design of these GPU architectures. Okay, yes?
So I'm just thinking of the example, this example here. So let's say after that fixed instruction, we're trying to get something from memory. So we wait to get something from memory because that's slow. Once we've gotten that thing from memory and presumably loaded it to the register file, 2 questions. A, how do we guarantee that the threads in the middle aren't using that portion of the register file for something else? And B, how do we know essentially that we're done fetching? And how do we know that this thread block, that this warp is available for execution again?
That's a great set of questions. Okay, so I'll answer the first one, and I'll try to answer the second one. So his first question is, well, okay, let's say at this point 6, instruction 6 is going all the way to memory, and it's going to take 1,000 clock cycles. Okay, but this warp here has a bunch of stuff in registers. I've got a bunch of values that are somewhere in that SM. Now, what happens? Because I'm going to, for 1,000 clock cycles, like way over here, is the next point that I'll be able to execute 7. Well, what we have to do by design is we have to keep all that state in the register file until the point that we can complete that warp. Okay, seems onerous, but that's what we have to do. Okay, there's no context switching in these GPU architectures. There's no context switching because context switching always takes time, and we need this warp scheduling to happen in an instant. Okay. Let me move on. Okay, there's much more to discover. We're going to spend a lot of time on this over the course of the semester. Okay, so point I want to make here. Warp, 32 instructions. Okay. all the threads within that warp are actually going to execute the very same instruction. So again, we're keeping the hardware super simple. So what we're going to do is we're going to force them to execute the same instruction, which is going to complicate things as I'm about to show you. It's not so bad when we're doing things like vector add, but when we're doing things that have some control logic in them, actually vector add does have some control logic. We can come back to that. What happens is there's this issue of anytime I have an if statement in my code, or any kind of control in my code, now I've got threads that might want to do this versus threads that might want to do this. And if the threads within the warp execute the same instruction, then what's going to happen is some are going to sit idle while a bunch of threads do this, and then the others are going to sit idle while a bunch of threads do that. This whole idea is called control divergence, or sometimes we call it branch divergence. Okay, so I'll give you an example. So let's say in our code we put thread index x mod 2. Okay, so that is every odd thread will execute whatever is in the brackets over here. And every even thread won't. Right? That's just what that logic says. So here, 50% of the threads will execute something and 50% of the threads will not. By the way, this is dangerous based on what I just said, because if I execute this and I put it in my code, what happens? What have I done to my GPU performance? You said the right thing. Yes, go ahead. I'm dividing it in half. I'm wasting half the performance of my GPU. Write that in there. Right? Because every thread block, every SM, I've got lots of threads, they're all being executed by the GPU. Right? So now I need to deal with that because it seems innocuous to do that. In fact, common. We may want to do that, and we will. So one of the optimizations that we need to think about when we code is to remap our control so that it's control divergence friendly. Okay. So for example, I could take that code. So again, let's think about our vector add example. Just a bunch of threads. And for whatever reason, I decide to put that in there. So now, half the threads are going to be idle. By the way, how long will they be idle? For those threads that are idle, how long will they be idle? Yeah. For as long as it takes to execute the code that's in there, right? So whatever I put in there, the threads that are active will execute that stuff. The threads that are inactive will have to wait until all the threads are done with that. Okay. What if I had an if-else? Then what happens? Yeah? In fact, it's all sequentialized. Okay, so what's going to happen is, okay, first we'll deal with the if. So half the threads, or whatever fraction of the threads, will do nothing. During the if part, the active threads will execute. And now let's deal with the else. Okay, flipped. Okay, makes sense? And that's the whole idea here. And again, why? What's the benefit of doing this? Clearly, there's no benefit from this perspective, but why would the NVIDIA And by the way, this is broader than NVIDIA. The AMD architectures, even the Intel architectures, also have this idea. What do we gain from it? Yeah.
You only need like one instruction pointer, so you only have to fetch like one instruction at a time.
Yeah, and there's a power to that. So one single instruction across 32 operations, right? So there's an efficiency that comes from that that's very strong. I have to fetch less instructions, decode fewer things, dot, dot, dot. And then it's up to us, the programmer, to kind of work around it. It's a pain to work around it, but we kind of have to become very clever about how we do things. As an example, okay, so if I took this simple, all the even threads and all the odd threads, and instead, by the way, that's just half the threads, right? And instead what I decided to do was, well, I'm going to take all the threads, divide them by warp size, okay? And so now take the thread ID divided by warp size, and find all the even ones and odd ones. So instead of interleaving evens and odds, what I'm doing is I'm saying, okay, here is an even warp, here's an odd warp, here's an even warp, here's an odd warp. Now if I do it that way, why is it better? Yeah?
All threads in a warp will be executing, so as far as throughput is concerned, it's still the same as if you didn't have. There's no divergence between threads.
There's no divergence, right? So now either the whole warp executes nothing, but it does it immediately. I'm not waiting. Or the whole warp executes something, and then it's doing real work. Okay, so there's a strong benefit to that. And whenever we can, in fact, we'll see some very good examples of this throughout the semester. We're going to try to remap what we do using this idea. Okay, any questions about this? Yes? Divergence? Let's take one more crack at it. Okay, so I'm going to maybe draw it out a bit. So let's see. So let's say I had some code. Okay, so I'm going to check a condition X, whatever that is. And if X is true, I'll do A, otherwise I'll do B. Okay, and this is in my code. This is part of my CUDA kernel, and it's doing whatever it's doing. Okay, so when this CUDA kernel gets compiled into code that's going to execute on the hardware, you can think of it as first we calculate X, and then there's some stuff to do A, and then there's some stuff to do B. Okay, notice I didn't put any branches in here. It's by design. So this code here, this stuff in the box, just again to be very clear, we can think of it as the kind of the instructions that result from the C code. And these instructions are what will execute on the CUDA hardware. Okay, so all the threads will calculate X, right? So they kind of go through, they all calculate X. Clearly, they're all calculating their own individual version of X. Otherwise, it wouldn't make any sense. It wouldn't make any sense. Now, based on the outcome of X, either the results of A will matter or the results of B will matter. Okay? And what does that mean? Well, what we can do, conceptually think about it this way. That if X is true, only then will we store the results of A into the registers, or memory, or whatever, or we'll store the results of B. This idea is called, it has a concept, it's called predicated execution. Okay. And sort of think about it as a bit that says, should I keep the results of this instruction or should I just throw them away? Is this making it clear? So that's what the threads will execute. Meaning they will all start executing the same code, and based on the result of X, only certain instructions will matter. Make sense? That's exactly what happens here. Okay, down at that low level. Okay. Now let's kind of put all this together. Remember, I said that, what are we trying to do? We're trying to load up the GPU with lots of options. The more options the GPU scheduling mechanism has, the better our efficiency of that GPU. Okay, so remember we were doing that RGB to grayscale, where we had the 2D image, and we put on that 2D image these 2D blocks, and some of those blocks had work, and some of those blocks were on the fringe, on the boundary, ... Okay, let's kind of revisit that, and kind of approach it this way. So we have a choice. So we've got the image, and we can use an 8x8 block, we can use a 16x16 block, we could use a 32x32 block. What's the advantage? Well, let's do some math here. So let's assume for the moment that the GPU has a limit of 1536 threads on an SM and up to 8 blocks. Okay, these are hardware limits. Any more than that, the SM just wouldn't be able to take any more, any additional work. So if we take and use the 8x8 choice, then what we're going to have is 64 threads, 8 times 8. Each SM can take 1536 threads, which means 24 blocks. Get mapped at most onto each SM. Okay. But each SM can only take 8 blocks. That's a limit, so I can't put 24. So at this point, what I'm going to be limited by is the number of blocks that I can map, and I'm only going to get 16 warps on each SM, which may be enough, may not be enough. I kind of go through all the other options, and what we end up with is, hey, the 16x16, I'm at the full thread capacity of the SM. That's actually quite good. I've got 1536 threads, lots of warps, the maximum number of warps I could have, lots of choice, right? So here is an example of how we're going to make that determination of block size. Okay, make sense? Yes? Ultimately, it's the number of threads. Yeah, which is this, just the number of warps. Really, it's the same. Right? Because that gives the GPU scheduling hardware the most choice. Okay, now, this is like the beginning. You're going to do this over and over again as we go through the various MPs. Okay. Any questions? We're going to put this aside and we're going to return to some real CUDA examples next. Yes?
Since each block is executing, since each block is mapped to an SM, if we have multiple SMs, that means multiple blocks can or works for multiple blocks can execute concurrently. So in some scenarios, wouldn't it be better to have more blocks or more parallelism among multiple SMs?
Yeah. Okay, so there are cases, right? I guess maybe I simplified it by responding, we're always trying to maximize the number of threads. Depending on what the threads are doing and why they're stalling, sometimes we may want to have more blocks. Okay, yeah, sometimes. Yes? Can we manually change the number of threads that a warp has? No. No, it's a fixed part of the hardware. In fact, NVIDIA claims that it's a architecture-specific parameter. But for every architecture they've had since the very beginning of CUDA, it's always been 32. Yes?
So, if you're writing like real code, how would you get these numbers and like pick the?
Good. So how would we know, like, what is 1536? Right. That's something that's part of the hardware, or you know. So you can query the GPU. Okay. You can use an API command like query. I should know this off the top of my head. Compute capability. Okay. And it will return a data structure where you can find all these things about the GPU, if you need to know. One question, and then we're going to move on. Yes?
Why do we have decreased friction on the number of blocks? I mean, that's completely not related to
Oh, sure. So his question is, why would the SM have a maximum number of blocks that it can support? And it has to do with this simple fact that for each block that we put on the GPU, we have to allocate a number of resources so we can do that zero overhead scheduling. Remember somebody asked, okay, if my warp is eligible for execution 1,000 cycles later, where's all the data that it needs? We have to keep it all resident. So we have to do a pre-allocation of all that for each block that we put on. Okay. All right. Let's put this aside. It'll become much clearer to you as we move on. And we're going to switch gears now and start to talk about the next portion of this. In fact, it's, that question that he just asked leads in nicely to this. Okay. So, again, the way we think about this primarily is from the notion of a thread. I've got a thread's got to do some work, and the kernel is just really how we're organizing these threads. Now, it turns out that the SM, has a bunch of resources that thread can access. Registers, memory, shared memory, global memory. And just like with our C code, what we can do is we can put values in those different memories. So we can put values in registers or in shared memory, constant memory. The next few lecture topics are really going to be around the use of these memories. Now, typically when we think of a thread, when we're writing, say, C++ code, we almost never think about the memory. Memory is just an abstract thing. Int x. It's just an integer. I don't care if it's in the register file, in the cache, or in the memory. It doesn't matter. It's just an integer. Now, in the CUDA world, we have to think about it. It has to be explicit as to where that thing lives. Okay, so part of our work as a programmer is going to be thinking about where that memory object lives best. Okay, and these memories all have different characteristics. Small and close versus large and far away. It's kind of the principle. So registers are close. They're 1, 2, few cycles away. Shared memory, which we will talk about extensively, is, say, 5 to 10 cycles away. Global memory, which we've talked about already, right? It's the place where we put, it's the off-chip DRAM that's on the GPU board itself, 500 to 1,000 cycles away. And then another type of memory, constant memory, which is also nearby, relatively. So we're going to manipulate all of these memories at some point this semester. And again, the game we're playing is those things that we use frequently need to be close, and those things that we use infrequently can be far. Okay? With that in mind, I want to motivate everything with an example. Okay, so let me take a quick digression here and just kind of elevate in your mind the importance of matrix multiply. When I was a student, kind of in your shoes, I remember taking linear algebra, which seemed, kind of interesting, and it wasn't that conceptually difficult. But I instantly forgot it, thinking, oh, I'm never going to need to know this stuff. I probably sold the textbook the instant I could sell it after the semester was over. Then I would say, after that, after I finished, I was a chip designer, designing chips for a while, not using matrix multiply. Really worried about making individual multiplies fast on the chips I was designing, and instruction pipelines fast. Not even thinking about matrix multiply, directly anyways. And then, many years later, I got involved in a company that was building a chip that was, at the time, the world wasn't thinking multi-core, and we were building a 40-core and then an 80-core chip. And the primary use case for that chip was physics simulation, which, at the end of the day, was massive matrix multiplies. So that chip kind of reintroduced me to this whole idea of linear algebra. Like, okay, it's important, got to understand it, got to think about what this here means, embed that computational pattern into my mind. And from that point on, I don't think I could leave this, because it just keeps appearing over and over and over again. No longer for the sake of doing physics simulation, but now for the sake of doing deep learning. Right? This idea of a matrix multiply, it turns out, is at the core of deep learning. So I think for all of you, I will safely say, linear algebra is a thing that you will use, even if you're doing things that you think aren't related to deep learning, because computer architecture is about deep learning. Algorithm design is about deep learning. So this pattern is something, what I'm saying in kind of a long-winded way, is like the thing that this generation here, needs just to deeply understand. Okay? And let's jump into it. So what we have, let's make it super simple to start with. Okay? Because what we're going to do is we're going to take the idea of a matrix multiply, and we're going to create a C version, simple sequential version, and then we'll create a simple CUDA version. And that we can do today. So we're going to start off simple. The simple idea is we've got two matrices. They're square matrices, M and N. and they're width by width. So everything is simple here. And we're going to compute P, which is M times N. And because everything is square, P itself will be width times width. Okay? So from the perspective of the computation, what we're doing is we're calculating the individual Pij's of the output matrix P by doing, by iterating through this internal variable K, which is really essentially doing a dot product of the two vectors that are in M and N. Let's give you an example. Okay, we'll give you another view of this. So here's the output matrix. Here is M, and here is N. So let's get a little comfortable with this diagram. So here's the output matrix, P, width by width. And for any element of P that I want to calculate, let's say this element here, what I will do is I will take the corresponding row vector of M and the corresponding column vector of N and essentially compute the dot product to generate that element of P. Okay, so what does that mean? So what it means is I'm going to take the individual elements of M one by one. So this element of M multiplied by the corresponding element of N, add it to this times that plus this times that plus this times that, and so on and so forth until I've calculated the entire dot product. Okay, so again, so I'm going to take each of these, multiply them together, and then add all those individual elements together in order to calculate this individual element of P. Okay, how many multiplies will I end up doing? So again, my width, this row vector and that column vector are width. How many multiplies do I end up doing? Yeah. Just for one element. Let's make it simple. K, or width. K is the iterator, but width is the total, right? So width minus 1, right? No, width. Width. The adds are width minus 1. Okay, makes sense? So for each element out, there's a lot of work that we end up doing based on the size of the matrix. Okay, so now if I wrote this in C code, maybe it'll take you, if you had to do this on your own, maybe 5-10 minutes to do it, right? Not an hour. By the way, if you were given this and it ends up taking you an hour, don't panic, but spend some time really honing your skills on doing this kind of algorithm transformation, okay? I would expect it to take 5-10 minutes at most. What is the idea here? So what I'm going to do is I'm going to iterate essentially through all the elements of P. So that's what the outer loop int I equal I from 0 to width minus 1. What that's going to do is it's going to iterate through all the rows of P, and then the next loop, the J loop, is going to iterate through all the columns of P. So those two outer loops are just kind of going through and telling me the Pij's. So once I know which one I'm calculating, which I know because of those two outer loops, I do the inner loop, which is the dot product. So for the dot product, what I need to do is kind of iterate through all the elements here, which happens to be the same as all the elements there, and just go through and calculate what I need to calculate, right? Which is to say, I really want to get the element of M, which is A, the element of N, which is B, multiply them together and add them to the sum, and compute just go through that loop, the K loop, until I've calculated the sum, and then store that at the appropriate Pij. And then we're done. Right? Pretty simple, I hope. Any questions on the C version of this? Yeah.
Like, when we go to, like, parallelize this, like, what's the... I guess because, like, you have to, like, there's, like, the vector add from lab 1, and then there's also, like, the multiplication. Because, like, my question is, like, is there a possibility where you could try and do too much and actually slow it down?
Oh yeah. Oh yeah. Yeah, so let's do this. Let's not overcomplicate things to begin with, right? And in fact, that's always the right strategy, from whether it's this one or things you're going to do 3 years from now. Let's start with a simple approach. And I mean, the observation we can make here is, again, let's look at P. Where is the parallelism in P? Yeah?
Each spot within P can be calculated independent of all the other ones.
Purely simple. Okay, we're going to make that simple statement. If you didn't hear it, what he said is, every element of P is independent of every other element of P. Let's start there, okay, which is to say that let's have each thread just work on an element of P. Okay, and then we'll go from there. So let's already, I'm hoping that in your minds you're trying to figure out how I'm going to do that. We're going to do it together, okay? But before we go and talk about the parallel version, let's make sure everybody's clear on the sequential version. Anything here seem odd? Now's a good time to raise your hand. Yes.
I just wanted to clarify his previous question.
Yes.
What he was asking was that the first two for loops is the P computation that's independent. What he said was, since this third for loop is also kind of independent, could you also do like a nested parallelization of that?
Absolutely.
Okay.
Yeah, absolutely. But my point was, let's not get too complicated yet. In fact, you could look at this thing and say, wait a minute, what is that inner loop doing? Okay, and if I wrote it out, just to make it clear, it's not a vector add. Right? It's not what we did in lab 1 by any means. In fact, it's important for us to make the distinction, right? Because what it's doing is really, let me just write it out a bit. Okay, so M0 right? This is what it's calculating. I've removed one of the dimensions, and hopefully that doesn't confuse you. But for AP, NAP, that's the computation that's happening in that innermost for loop. You might look at it and you might say, well, there's nothing parallel about that. Right? If it's just a sequential, well, I'm applying the word sequential liberally, but it looks like a sequence of multiply adds. Does it make sense to parallelize that? Doesn't seem easy to do, But is it even parallel? We know because somebody asked, we went through this discussion before, and it turns out, yeah, this is parallel. Not fully parallel, but it's parallel because I can do this independently of doing this. So I can somehow chunk this into a way that it is parallel. But we're not going to go there yet, okay? Again, let me make sure we unwind and say, we're just going to try to parallelize the simplest part in the simplest way that we can for now. Does that make sense? Okay. Let's move on then. So, because it's a 2D problem, 2D matrix multiply, what we need to do is kind of map it into the CUDA thread structure. Right? What we have to do is, we have to pick a block size. And we're going to keep the two-dimensional structure in the way we pick the block. Okay. So again, what we're saying is, each thread calculates one output element. So if my width is 4, so I've got 4 threads by 4 threads, 16 threads altogether, I could organize them as blocks of 4 threads. So I've got these 4 threads, these 4 threads, these 4 threads, these 4 threads. That constitute that full matrix, the full matrix multiply. Okay, so, kind of said another way, what we're going to do is we're going to take the output matrix P and we're going to tile it with these blocks. Okay, for the moment, we'll keep things simple. P is square, things are powers of 2, makes for nice code, at least in lecture. Right? So, slightly bigger example. This is a 16 by 6 or 8 by 8 output matrix, and what we have done here is put 4 threads in a block, so there are 16 blocks overall, right? Hopefully you can extend this into larger sizes pretty easily. So with this in mind, oh, by the way, so same example, here what we've done is picked a block that has a width of 4 as opposed to a width of 2. So now there are 4 blocks where each block has 16 threads. Okay, so the first part of this is to think about how we map these dimensions onto the input. So the input we're providing our kernel is some m, n, and p with a width, right? Just a single parameter, aside from the memory, of how big the problem size is and its width. So what we would do is we would have to create an execution configuration that tells us how many blocks we have in each dimension and how many threads we have in each dimension within each block. Okay, and it's quite easy. So what we'll do is we will take the width and divide it essentially by block width. That's the number of blocks we're going to have in the x dimension in the grid. And then the same thing in the y dimension. Now, because C, C++, the integer to floating point conversion is finicky, we just kind of did this code here to make sure that we don't lose and generate an error where there's some boundary condition on the floating point conversion. If you don't understand that code, don't worry about it. It's just very C++ and C oriented. Bottom line, what we're doing is we're trying to calculate how many blocks in the x dimension and how many blocks in the y dimension, just by dividing by block width. Okay. Then likewise, we need to dimension the block, which is easy because it's just, here's the block width, and here's the block width. So when we want to execute our kernel, our matrix multiply kernel, we just provided the dim grid and dim block as we've calculated, and we're good to go. Okay, that's the easy part. Hopefully that made sense. So now let's talk about the kernel itself. Okay. So now, when we start writing this, the perspective we need to have is, okay, I am calculating one element of P. That's all I got to do here. Which means that if I go back to my C code, the outer two loops are gone. I don't have to worry about the outer two loops. It's really the inner loop that I need to put here. Okay. Now the first thing I'm going to do, and I told you this last time, is I want to calculate the output coordinates, the row and the column of the output. Right? So I'm calculating some element of P. I will figure out its value in this code, but I also need to know what is that Pij that I'm calculating. And of course, I don't have those the for loop for I don't have the for loop for j, but what I do have are the thread index and the block index. And from those two values, I have to recreate row and column. Let me give you a few examples. Okay. So we've got this thread block trying to calculate P00 and P01 and P10 and P11. Okay. And at this point, right, let me emphasize to you, what I'm just trying to do is enable each of these threads to figure out what their output coordinates are. P00, P01, P11, row, comma, column. Okay. So let's kind of look at this right here. In fact, let's start with maybe this thread that's calculating P00 to start with. Okay. So again, what do I have? I've got block index, I've got block index X and block index Y, block dimension X and block dimension Y. So in order for me to figure out what column I'm operating on, what I will do is take the block index X of the thread and multiply it by the block dimension. Why am I doing that? Because the block index is telling me where I am in this way. Okay, so it's telling me kind of which column am I going to be in. Then I multiply it by the dimension, right? It just kind of chunks it along. And then thread index. That's the way I'm going to recreate my column. And likewise, I have to do that for the row. So let me pause here and let me emphasize to you that this is simple. There's details involved. And for a good majority of you, you're going to get sloppy and you're not going to pay enough attention to getting this right. When you do your MPs, some amount of the bugs you're going to introduce is just around this mapping from thread index, block index, into the appropriate output coordinate. Okay, because this is a 2D example, we could have a 3D example or a 4D example. So let's just kind of see one more example here. So this is block 0, 0, this one right here, which means that block index x and block index y are both going to be 0. Thread index x will be 0, 1, and thread index y will be 0, 1. Okay, so same thing here. Now we're looking at this block over here, and everything changes because block index x and block index y have changed. Okay. So moving on here, what that means for us is once I calculate the row and the column, it's super simple. Because what I'm doing is now just going through and doing that inner loop. Okay. Where that inner loop is essentially the k loop, right? So it's k, 0 to width. Just take the element of m, take the element of n, multiply them together, and accumulate them in p-value. And then once I'm done, store it, and voila. That's all it takes. Of course, what I have to do is, based on row and column, make sure I get the right position of both the input and the output values. But again, it's just the conversion of the 2D structure into a linear form. Okay, there we go. CUDA version of matrix multiply that does it in parallel, right? All the threads are calculating now individual elements of the output matrix P. I do have to add row less than width and column less than width for obvious reasons, right? What's the case here that we have to worry about? Yeah? Good. Let me just paraphrase what you're saying. She said that in the case where width is not a proper multiple of block width, right? So there we go. Any questions on this CUDA version? Yes?
What is the benefit of that?
We could, but again, if we have one block, then we have one schedulable parallelizable entity, right? So that one block ends up on one SM and doesn't go across SMs, right? So, if our GPU had 1,000 SMs, well, we're not really fully utilizing at that point. Good question. Yes?
Is it possible to design the thread so that we can get rid of this
Get rid of what?
inner loop? Is it possible to get rid of the inner loop?
Oh, is it possible to get rid of the inner loop? Meaning, can we have the threads do something smaller than the inner loop? Yes, the answer is always yes, we could. Again, what that would require is going back to what I was saying earlier, which is somehow we'd have to parallelize this, because this is what each thread is doing, right? That's the computation that each thread is doing now. And if I don't want the thread to do all of that, then I have to figure out how to divide this up amongst threads. Which we can, and we will do that for, lab 5 or 6. 5.2, actually. Yes?
For the two threads, when we send two matrices in the CUDA and the matrix multiply,
Okay, so your question is, when I execute a matrix multiply in Python that's running on a CUDA GPU, is this what's happening? And the answer is yes. Actually, it turns out that this simple version doesn't work so well. I'll show you on the next slide. So we have to do a bunch of more things in order for this to work well. And that's what the CUDA version of the matrix multiply will do. Okay, so we're writing that code in this class. Okay, so why doesn't this work well? And I'm going to give you a hypothetical for the moment. So let's say, by the way, so when we're executing this code, let me go back to the previous slide, just so that it's all clear to us. Float M, float N, and float P, star D underscore M and dot, 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 right? I'll just simplify them. What are those? Those are pointers, clearly. To what? Yeah? Good. So she's saying that those are pointers to wherever we allocated using CUDA malloc, M, N, and P. In other words, they're pointers to the GPU global memory. This is the off-chip memory that's next to the GPU chip on the GPU device itself. Okay, so M, N, and P are there. So when I do this, for example, what's happening? It's accessing global memory. Thousands of cycles, or 1,000 cycles, let's say. Same thing's happening there. Okay, let's take a look at this here. Because if we have a big matrix, all the work that's happening is really just this one line of code. All the other stuff is overhead, right? Because let's say width were 10,000 or 100,000. I'm just doing 100,000 versions of this over and over again, and that's what one thread does. That's really where all the work is. So what's the work? Load, multiply, add, store. Actually, it's a register, so sorry, no store. Load, multiply, add. And by the way, if you're an architect and you're thinking about designing hardware, load, multiply, add, that's a common theme. So I'm taking two values from memory, multiplying them together, and adding them. So for each load, I have one operation. Make sense? Right? Because two operations, the multiply and the add, and the load and the load. Let's come to this. Let's say the particular GPU that we're working with has a peak memory bandwidth of 150 gigabytes per second. It's hypothetical. In fact, today, it's maybe about 10 times that for the highest end GPU. But it's still, same thing will apply that I'm about to say to you. If we go through all the arithmetic around this, 150 gigabytes and two memory accesses per two floating point operations, the actual code will run at 25 gigaflops. 25 giga floating point operations per second. That's just counting the multiplies and the adds. We're not going to count the loads. They're not doing any work. Okay? So if the peak of the GPU that we're dealing with is 1,000 gigaflops, or 1 teraflops, And we're severely limited by the memory bandwidth here, right? We're throwing away a significant chunk of the performance sitting idle, waiting for memory to deliver M and N in this case. Make sense? So clearly this is not the way we would do the matrix multiply. We've got to think differently about it. And that is what, we'll introduce it next time, that is what the essence, I would like to say the essence of CUDA programming is really to figure out how to get around this particular issue. Okay. Any questions? Good. Well, I feel like we've covered a lot of ground today. Why don't we end now? And when we get back on Tuesday, we'll deal with this. Okay? Thank you.
Excuse me, Professor. I have a question.
Yeah, why don't we do this? Why don't we go outside? Yeah.
Hello, hello. Yeah, just a sec. Let me connect. Hello, hello. Hello, hello. Yeah, I think it's connected. Hello, hello, hello. Testing. Hello, hello. Good. All right. Oh, hello, hello. Test this mic. Hello, hello. Good.